Tg, the gas temperature, the TIT, this is TIT, but we need to be careful with what we call the TIT. I mentioned that yesterday with the combustion chambers. So you have everywhere there around Tg, and Tg is impacting the material. It's eating up the material, and you extract this heat thanks to this circulation of air that you have here inside. For example, you have small channels like this. You can have 1, you can have 2, you can have 10. It depends on the technology. And so this cooling air is seeing, of course, its temperature increasing, because here you extract a first quantity, the temperature is higher, it's going higher, you extract a quantity, it's higher, higher and higher, and of course here at the tip, Tk tip is much higher than the Tk hub, okay? Maybe also the Tm will not be the same. Of course it will not be the same, because if Tg is the same everywhere, here you have a lower Tk, so you will have a lower Tm, because the air is cooling better the material. And so Tk will increase with R, and Tm will also increase with R, considering, for example, that Tg is a constant. Yesterday I've seen that Tg is not a constant. I've said to you that there is a profile of temperature, but I'm not mixing everything, so in the model, and here I'm considering that Tg is a constant. And the cooling technology that we have here, this is what we call, so with the, let's say, tubes or channels, the cooling channels that you have here, this is just what we call convection cooling, because it's just by pure convection of air inside one or different channels that you are cooling down the material. This is Tm that you are cooling down with a convection technique. And if you write the equations of what I have just represented there, what do I have? You see that I have Tg giving heat to Tm. The heat given to Tm from Tg is proportional with the difference between Tg and Tm. And this is also proportional with the contact surface, and the contact surface is proportional for each slice that you are considering in the radial direction with dH, and I also name the length, so the contour that you have here, I call that Lg. And this is also proportional with Hgm, that I will call from now on Lg, but this is the heat transfer coefficient by convection between the gas and the metal. And so the heat that is transferred from the gas to the metal is equal to this quantity. And then you have the air that is passing here inside, and the metal is giving also heat to the air. What is the transfer that you have between the metal and the air? This is proportional with the difference Tm, T metal, T material, minus Tk, T cooling. And this is also proportional with dH, the dH that you have here. And this is proportional with, if you have one channel, 1 perimeter. If you have two perimeters, if the channels are not the same, 1 plus 1. So the global perimeter of all these cooling channels, that I will call Lk. And this is also proportional with H, I would say, metal towards K, that I will call from now on Hk, which is the heat convection coefficient, the convection coefficient from the metal to the cooling air. And what's happening with this heat that is transferred from the metal to the air? This heat is going, let's say, away. It's leaving the system. Where is this going? Maybe mixed back with TG. So if it's going there, at a certain moment it will be mixed again with the air or the exhaust gases that are here around, that are at the temperature Tg. And so what's happening with this air flowing inside the blade? It is at the temperature Tk that will change. It is at the temperature Tk that will change. You can maybe also write that this is something like this, because it will be also depending on Tk up, that is a constant, and the derivative of a constant, this is equal to 0. And this heat that is transferred from the metal to the cooling air will give an increase in temperature of this air that is proportional to what? That is proportional to the mass flow rate that you have here. So m dot k, this is the total mass flow rate of cooling air, multiplied by Cp of this cooling air. This is so the amount of, let's say, heat that is extracted from the metal by the air. And if at a certain moment this is constant, at a certain place we have a K that is constant, Tk that is constant, a Tm that is constant, and at every place of the system the situation is not changing anymore, that means that we have reached an equilibrium. If we have an equilibrium, so that means that we will have what? We have that the heat transferred from the gas to the metal, this is equal to the heat transferred from the metal to the cooling air, and this is also equal to the heat absorbed or taken away by the cooling air. And you have this triple equation that is governing the condition of cooling the air. So this is equal to this is equal to that. And you see also appearing the important parameters that we have in the problem. So of course, an important parameter, this is this one. Another one, which is this one. And another one, this is this one. But these are not really parameters, these are more variables. So what is your objective? Tg is given, Tm is also given, Tk is a variable. You fix this, for example, and your objective is to increase that by having this, let's say, also equal to a constant, for example. Or you could say, I'm keeping this equal, I'm reducing Tm in order to increase the lifetime with this that is constant, for example. But you have these three temperatures that can be managed in different way in function of the objectives you have. If you have a fixed geometry, this is not really a parameter. This is not really a parameter, okay? But you have other parameters that will be important. Where are they? I will indicate them in yellow. The first one is this one. The first one in this is this one. The second one is this one, HKLK. Another one, extremely important, is this one. Another one, of course, this is this one, because Tk will decrease if Tk up is decreasing. And there is also a very strange parameter, which is this one, that we can certainly discuss at a certain moment. The main parameters will be 1, 2, 3, and then we will have also this one. We will see that it's not easy to play with this parameter. And then we have this one, it is even more difficult to play with this fifth parameter. So these two ones are, we will see, not easy to take care of, okay? I will need certainly to speak adequately about this one, because we do not understand exactly today what are the consequences of this m.k. Why is it so important? I will introduce that later on. And if you look at HGLG and HKLK, so I indicated you, normally what you try to do, this is this, improve the TSFC, lower the TSFC, improve the thrust, improve the specific thrust, with this equal to a constant. So what will you have to do? You will need to decrease this parameter. That's clear, that if you want to take this constant with this increasing, the only solution, this will be to decrease this parameter. That means you are transferring less heat to the metal. But also, you have this parameter that can play a very important role. Because if you are transferring more heat to the metal, if you are able to extract more heat, it's also positive. And you see that just by writing, even not solving these equations, you understand how we will improve this technique. We will improve this technique, which is the C1, the convection. This is the first technique. We will improve this technique by C2, one of these two, and C3, the other one of these two. That's clear. And this is coming directly from these stupid equations. So if you are able to increase HK, LK, you will have a second step. And if at the same time, because you see that it's cumulative, you decrease at a certain moment HGLG, you will have a third step. And that will give you, let's say for each step, like this is easy in your mind, 100K, first step, 100, 100, 100, 100, always 100. And what are these techniques? HKLK. How can you increase that? So you can increase it by HK, O and LK. How can you increase HK? So you can increase HK, and you can also increase LK. HK, this is closely related with the Reynolds number of the cooling air. You know, H, this is proportional with the Nusselt number of the cooling air, and the Nusselt is proportional with the Reynolds number. So if you increase the Reynolds, you increase the Nusselt, you increase H. This is one solution here. So you look inside the blade is empty,